Hey folks, today we are talking about limits and continuity. I don't know if I like this better or not. It's taking up the whole, well, we'll see. Okay, so this is something we talked about at the end of pre-calculus. This idea of the limit is what the graph intends to do. So calculus is broken into two pieces. We've got the differential calculus. We have integrable calculus. And those two come together to form what's called the calculus. The calculus is the joining of those two calculi. Anyway, these two branches came together. They make the calculus. That's called the fundamental theorem of calculus, which we will get into at some point, but we're not there yet. So this idea of a limit, let's review what a limit is. So we're going to start off by looking at a limit based on filling in this chart. Now, I already grabbed my calculator and figured out these values, but all I'm doing is typing in my function is f of x equals x squared. All I'm doing is inputting 2.9 in for x. So 2.9 squared ends up being 8.41. 2.99 squared is 8.9401. 2.999999 is 8.99440001. And then we're going to look at this. Then we're going to start plugging in some values on the other side of 3. So, well, I'll talk about that in a minute. Let's just plug and chug. So 3.1 squared is 9.61. 3.01 squared is 9.0601. And 3.001 squared is 9.006001. All right. So we're going to have to be able to figure out the limit 3 different ways. From the graphs, from the equation of a function, from the table of a function, which is what we have here, and from the graph of a function. So the best way to figure out the limit as we're approaching 3 in a table is to just kind of look what's happening as we get closer and closer to 3 from each side. So what do these values tell us about f in the neighborhood of x equals 3? So in other words, if I look at these 2.9, 2.99, 2.99999, what is my x value getting closer to? That's what I said, my x value. My x value is getting closer to 3, and my y value is getting closer to 9. 8.4, 8.94, 8.994. You could guess what 2.9999 would be. Everything's getting closer and closer to 9. Now let's look at this from the perspective of the other side of 3. So look what's happening to my x values, 3.1, 3.01, 3.001. Those are all headed closer and closer to 3. My function values, my y values, 9.61, 9.0601, 9.006001. You could probably guess how this is moving, and it's heading towards 9. So what would we say here? What do these values tell us about f in the neighborhood of x equals 3? They're telling me my y values, my function values, I'm going to put in parentheses in here y values. We just don't say y values anymore. We know that it means y, but we don't say y value. We now say function because we're a fancy mathematician. My function values, they're not 9. I'm talking about the numbers that are in the neighborhood of 9 are getting closer and closer to what number? 9. They are approaching. My function values are approaching 9. Based on the chart above, what do you think the value of f of 3 is? So if I said to you, this is the pattern from before 3. This is the pattern after 3. What do you think is happening exactly at 3? Well, I certainly would guess that it is 9. I would guess f of 3 equals 9. What is the value of f of 3? Well, we have a function. F of 3, plug it into our equation, would be 3 squared. 3 squared is 9. And you might say, okay, well, this is kind of boring. Well, it is boring when our function is what we call continuous. So if you think of the graph of x squared, there's no weird things going on with x squared. So this is a continuous function. So what we call the limit, the values that our graph is approaching. Let's go back and put this in parentheses. My function values are approaching 9. This is what we call the limit. Now, in a continuous function, the limit and the actual function values are going to be the same number. Let's look at one that's a little bit more interesting. So we've got g of x is this function. We're allowed to use our calculator. I already did it for us, so let's just use my numbers. 2.9 plugged into this is 8.41. 8.9401. 8.994001. Oh, I did put an extra 4 in here. Up here, I did not need to. This is just a 0. Hopefully, you're noticing that this looks kind of interesting. It's the exact same function values. And then we look at this one. 3.1 turns out to be 9.61. 9.0601. 9.006001. All right, now let's see what's happening here. What do these values tell us about g? Now they call it g because this is a g function in the neighborhood of 3. When we're getting closer and closer to 3, what are our function values? They are approaching They are approaching 9 again. Based on the chart above, what do you think the value of 3 is? Well, I would guess not f of, g of 3 equals 9. Okay, so what is g of 3? Well, let's figure that out. I'm going to now plug in 3 into my function here. So g of 3 would equal to 3 cubed minus 3 times 3 squared over 3 minus 3, which turns out to be 27. Take away 3 times 9 over 3 minus 3, which is 0. 3 times 9 is 27. 27 take away 27 is 0. 0 over 0 is undefined. So now what happened here? This is undefined. According to our table, what was happening to our x or y values as x got closer to 3? Our x values were approaching 3. Our y values were approaching 9. But when we actually got there, when we actually plug in 3 into our function, we get an undefined value. We get a number that doesn't exist. This is what we call an indeterminate form. 0 over 0 is an indeterminate form. And what it means is your graph has a hole. So our graph has a hole. This function has a hole at x equals 3. And let's go ahead and I'm going to prove that to you by graphing it on my calculator. So my function is y equals alpha, so I can get a top and a bottom, x to the third minus 3x squared over x minus 3. Now wait a minute, that graph looks familiar. What is that? That's a parabola. It looks just like our parabola up here, right? It looks just like x squared. But the difference is when I trace to 3, I do not have a y value. I have a y value at 3.1, I have a y value at 2.9, but I do not have a y value at 3. That's because we have this tiny little hole in our graph. So we've got this thing that's called a limit, and we've got this thing that's called a function value. The limit is what our graph is approaching. So let me kind of zoom into my window here. I'm going to take this window, and I'm going to make it just in the neighborhood of 3. So I'm going to go from 2 until 4. And I'm going to go, let's say, from 5 until 15. Here's my graph. Look at what happened. When I zoomed in a little bit, you see that right there? There's a tiny little hole exactly when I trace to 3. It doesn't show up. If I go to 3.1, it's just to the side of it. 2.9999 is just to the side of it. But at 3 exactly, there's nothing there. There's a little tiny hole. Now, this equation looks super complicated. But in reality, it's a simple equation that has a hole in it. And so we have two ways that we can talk about what's happening at 3. We can talk about the actual function value. What is the y value at 3? There is no y value at 3. Y does not exist. But what we can also say is what is supposed to be at 3. What is the limit? And the limit is what the graph is headed towards on either side. So mathematically, that's interesting to us. Even though there isn't an actual point, we could still predict, if I had this function as a model of a situation, some sort of maybe experiment that I collected data on, even though at specifically 3, this model wouldn't work, I can use this equation to predict what should be happening at 3. So is there a way to mathematically communicate the result from the chart up above? That's this thing called a limit. We would write this up, the limit of g of x as x approaches, what are we going closer and closer to? 3 would equal 9. This is what we call limit notation. This is saying what is happening to my y values as x gets closer and closer to 3 from both sides. And from our graph, as x gets closer and closer to 3, our y values get closer and closer to 9. All right, so let's get into this. We're going to explain this all over again in the next page. So Corpy gets into more details here, talking about what a limit is. Hugely important idea. The limit is the foundation. I think Newton called them, so Gottfried Leibniz and Isaac Newton came up with the calculus at the same time. And Newton's idea of this thing called the limit, I think he called them fluxions, which is kind of a weird thing, but it's this idea of, can you predict what's going to happen even if you can't figure out directly what is happening at that moment? Okay, so the interruption, I don't know why he's got restricted area, aliens. The interruption to the flow of the graph of G in example 2 is called a removable point discontinuity. Or, in normal terms, we call this a hole. Now, if you call this just a removable discontinuity, you could just call a hole a removable discontinuity. I don't remember seeing this phrase a whole lot when it comes to the AP test. But anyway, okay, so how did we know that it was going to be a hole? How are you supposed to, without using a calculator, how are you supposed to predict if you've got a hole or if you've got a other type of discontinuity? It came from what happened when we plugged it in. Do you remember what we plugged in? When I plugged in 3 into my function, I got 0 over 0. 0 over 0 is an indication that you have what's called an indeterminate form. Which, in normal language, means that you have a hole in your graph. You're missing one point somewhere. So there's 3 scenarios that you're going to see when you try to direct substitute into an equation. There's 3 things that could happen. You're going to get, well, there's 4, I guess. You could just plug it in and get a number, and then you're fine. That's your number. But the things with 0, there are 3 different things that could happen. You could have the top of the equation equal to 0 and the bottom not equal to 0. Well, stop and think about this. What if the top is 0 and the bottom is some other number? What's 0 divided by any number? 0. This makes a 0 on your graph. Now remember, we also call 0 x-intercepts. You might see solutions. You might see roots. All those things are another word for the 0 of the graph. So if I get 0 over something that's not 0, I would get a 0. I'd get an x-intercept. What if the top is equal to 0 and the bottom is equal to 0 when you plug in, let's say, you plug in 3 like we did in that equation, and they both turn out to be 0 over 0? That means my graph has a hole at that x value. And then the third case, so I have a 0 on the top, not a 0 on the bottom. That's a 0, because 0 divided by anything is 0. 0 on the top equal to 0 on the bottom. The zeros kind of cancel out, quote unquote, and it creates a problem, but it's just a little problem called a hole. What if you don't have a 0 on the top, but you do have a 0 on the bottom? This is a big deal. This is the worst thing that can happen in all of mathematics, is to divide by 0. When you try to divide by 0, it creates the worst thing that can happen to a graph, which is a vertical asymptote. Okay, so simply evaluating a function. This is a big idea. Simply evaluating a function at a particular value is insufficient for figuring out what's happening to your graph, especially with functions that have discontinuities. So what I'm saying is, if you just plug and chug, sometimes you get an answer that doesn't make any sense. So simply plugging in a value doesn't help you figure out anything about your function. And that's what we do. So to get around this situation, we do this to circumvent. So to circumvent this, we go to circumvent going directly to a location, to a point, all right? We look at what that is approaching from either side. This is what we call a limit. So if I can't directly just plug in a number, what I can do is look at what the graph is doing on either sides. And he talks about this in terms of a bridge, which I like. I like this idea. So the idea, the limit is a notion of motion. So the motion that he's going to be talking about is on a bridge, but we're going to translate that idea to motion along a function. So suppose you wanted to safely and smoothly cross a chasm in your car. What three things would you need? So what would we have to be able to get over a chasm? Well, we'd need a road. Coming from one side. So in other words, I'd need a road coming up to the chasm. I'd need a road on the other side. And most importantly, so I've got a road coming up. I've got a road going out the other side of the chasm. What do we need in the middle? We need the bridge. These things, this road coming from one side, the road coming from the other side, that's the function. That's this right here. Coming in from this side, coming in from that side, that's the road. And then the bridge is what's happening right there. For this function, our bridge is missing. Our bridge, which is the point, doesn't exist. So as we can see, the existence or non-existent of the bridge. So when he's saying bridge, he's saying the y value. He's saying the point. This is the point. The function value means the actual point. So the existence of the bridge, if the bridge is there, is totally independent. Is independent of the existence of the roads leading in from either side, which is what we call the limit. The limit is what the graph intends to do. So if I have a bridge, I could have a bridge without having the two roads coming up to the bridge. You could just have I don't know why you'd do it, but you could picture having a bridge just randomly in across the Grand Canyon, or maybe something a little bit smaller than the Grand Canyon. So we could have the two roads coming in and there'd be a bridge there. You could have two roads coming in, but the bridge fell down overnight, so there is no point, but the two parts of the graph come to meet. Or you could have even a crazier situation where they drew the roads here. They drew the road here, so the roads are headed toward each other, but then for some reason they built the bridge way back here without any roads leading up to it, right? That'd be a major screw up, but you could imagine that it could happen. It could be possible. Okay, so let's try to figure out how can we tell what our limit is just from the equation. And then we kind of led into it. I kind of already did this problem on the other one, or sorry, when we did the first page. So for this function, algebraically determine the coordinates of the removable point discontinuity. Then use limit notation to describe what's happening as the discontinuity is approached from either side. So what's that saying? That's saying that this graph, they're telling us, so they already gave it away, has a removable point discontinuity. When I say removable point discontinuity, that's a long-winded version of saying what? Hole. This graph has a hole somewhere, and we've got to figure out where that hole is. So let's go back to our rational function stuff, VA, HA, SA, remember? How do you determine where the hole is? Well, hopefully you figured out that it's the part that cancels. So g of x equals, I need to factor this. I can take out an x squared. That leaves behind x minus 3. On the bottom, I've got x minus 3. If you'll notice, we've got an x minus 3 on the top and an x minus 3 on the bottom. So there's a couple of things that come from this. There's a couple of things that we can now figure out. We can figure out that g of x is really just the graph of x squared with a hole at x equals 3. So what's interesting is if you have a function that has a hole, once you eliminate the hole, the graph will look exactly like what's left over, except you've got to remember that there was supposed to be a hole at 3. So we did this a little bit when we were making our sketch. Let's actually try to sketch this one. This isn't too bad to sketch. 2, 3, 1, 2, 3. Notice I'm not going to go up and down because I don't want to count off to 9. Okay, what family is this? This is the x squared family, the quadratic family, no shifts. So it's just a normal over 1, up 1, over 2, up 4, over 3, up 9. But what's happening at 3 is we've got a hole there. So our graph will look something like this. And then on the other side, I can use my symmetry of even functions to figure out what that part of the graph looks like. We have a hole. This is the graph of g of x. G of x is the same as the x squared graph, but with a hole at x equals 3. So what's the location of that discontinuity? So where is, this is saying, determine the coordinate of the removable point discontinuity. So the question is, where is the hole? What are the coordinates of the hole? Well, remember, the hole we know is occurring at x equals 3. So that's my x value. And if we try to plug 3 into this, what are we going to get out? Undefined. You're not going to get an answer out of this. So what we do instead is we cancel out where the hole is. This is the graph, so this will tell me where the graph was supposed to be. The graph is, the hole is at 3, 9. It was supposed to be at a height of 9, but because we had this discontinuity, because we had these canceling terms, that there isn't actually a point there. So if you ever want to figure out where a hole is, cancel out where the hole is in the equation. Whatever's left over, you can now plug 3 into that, and whatever that was supposed to be or whatever that is going to tell you what our graph was supposed to be doing at that spot. The second thing we're talking about is use limit notation to describe what's happening at the discontinuity. So remember, let's write this up properly first. This is saying the limit of f of x. That's saying what is happening to my y values as x approaches 3. So it says what is happening to my y values when we approach 3 from both sides. So when I approach 3 down here, and when I approach 3 down here, actually I'm going to do this in different colors. Maybe it's too late, but hopefully it'll show up. If I approach 3 from this side, my y value is approaching 9. If I approach 3, what would be a color that will show up? Maybe this green. If I approach 3 from this side, my y values are going down, down, down like that, and they're approaching 9 as well from this side. So the limit is what those values are approaching. The graph is approaching 9. The limit, my function was supposed to be at a height of 9. Was it at a height of 9? No, there was a hole there. But that's not what a limit is asking you. The limit is just talking about the roads. Where were the roads headed? If you said to me, let's meet at McDonald's, I could drive to McDonald's uptown. You could drive from your house to McDonald's uptown. We both would be at McDonald's, but overnight, let's say, the McDonald's somehow blew up. A meteor hit it. So there's nothing but a big giant hole there. But we're both at the same place. There's just nothing there. That's what a limit is looking at. The limit is trying to figure out, where did the graph intend to go? I intended to go to McDonald's. You intended to go to McDonald's. We got to McDonald's, but there wasn't actually anything there. All right, so here's our theorem. This is a notational thing. So let's get in. Let's circle these and try to highlight what this is talking about. So this is the limit. What is happening to my y values as x approaches c, and that little minus means from the left. So that little minus means look at your graph coming from the left side of c. In this case, c would have been 3, and the limit as we approach from the left would have been 9. Then we have this other one with the little plus. Let's go with orange here. This little plus, you could probably guess, means from the right. What is happening to my function from the right side? These two things have a fancy name. These are called one-sided limits. These are what we call one-sided limits because they're limits that only come from one side. So if we have a one-sided limit, and our one-sided limit approaches some value, we're going to call that value L. L stands for limit. So the limit from the left side approaches L. And if my limit from the right side also approaches L, so I'm going to highlight that L from both sides. If they're both getting highlighted, then we have what's called the overall limit, which would be L, the limit from both sides. So if I were to write a little note here, we would call this whole thing is called the overall limit. In other words, the limit from both sides at the same time. The overall limit is known as the limit from both sides at the same time. So this limit here, as x approaches 3, that's the overall limit. That was looking at the limits from both sides at the same time. I think we'll do these two and then we'll pause to make another video. Okay, so the theorem above essentially says that the limit will exist if and only if the two roads coming in from either sides are aligned with each other, which makes sense. If you are headed to McDonald's and I'm headed to McDonald's and we're both going, there has to be roads then that lead to the McDonald's, irrespective of whether there is a bridge connecting the two roads. So it doesn't matter if the McDonald's is actually there. If you're headed to it along your road and I'm headed to it along our road, my road, as long as we're both at the spot where McDonald's is, it doesn't matter if McDonald's is there or not. We have met. We have headed to the same place. So the limit exists if and only if the two roads coming in from either side are aligned with each other, irrespective of whether there is a bridge. So it doesn't matter if the bridge is there. The limit describes the y value where the roads are leading. The function value pertains to the bridge itself at that single point. Okay, let's take a look. Let's try to let's try another one. All right, so here's our function. We need to algebraically determine these three things. So let's first figure out what's happening at f of -1. Why is that really easy? You should be able to pause and do this on your own because all we have to do is plug and chug. So f of -1 equals -1 squared minus 4 plus 3 over -1 squared plus 3 minus 4, which equals, so that's 1. 1 take away 4 is -3. -3 plus 3 is 0 over, okay, all of a sudden my math voice is starting to listen here. This is going to be one of these scenarios on the other sheet. No, I put it over here. It's going to be one of these because I've got at least a 0 on top. So I know it's going to be either a 0 or a whole at this point. But I have to see what the denominator is doing. That's 1. 1 plus 3 is 4. 4 take away 4 is 0. This is what we call a whole. We know this graph has to have a whole, but that's not the question. The question is, what is f of -1? F of -1 is undefined. We don't know what 0 over 0 is as a number. And by the way, if you wanted to, you could write that f of -1 equals d and e. Those two things pretty much mean that, I mean, I guess I don't know if you can equal does not exist, but for this class, we allow it. We allow it. Okay, so now we can start to talk about the limit. So what's happening to my graph as x approaches -1 from the left? Well, remember, we said that there's a hole at -1. So what we can do is we can eliminate the hole, and then what's left over will give us our function. Remember up here? Once we eliminated where the hole was, we could just graph x squared and just remembered that there was a hole when x equals 3. So let's go ahead and factor this. F of x equals, this would be x plus 3, x plus 1. This would be x minus 4, x plus 1. Eliminate the hole, which makes sense. If I ZPP that, I would get x equals -1, which is what we just figured out doesn't exist. So what can we now say? So f of x is the same as x plus 3 over x minus 4, except with a hole at x equals -1. So whatever this graph does, this does the exact same thing except there's a hole here. But what's nice about this, I can now plug in -1 into that. So I can do The limit from the left would be -1 plus 3 over -1 minus 4, which would end up being, that would be 2 over -5, which we never would want to leave a negative on the bottom. So the limit from the left is -2/5. The limit from the right, I would also direct substitute. I can now plug this in to the pieces that are left over. So -1 plus 3, I guess we don't have to do it again. I guess I've already started writing it. But we know this is also going to be -2/5. So the limit from the left, the limit from the right, how do I know this is from the left? It's got that little minus thing. How do I know this is from the right? It's got that little plus thing. So the limit from the left and the limit from the right are approaching the same place. That means that my overall limit is -2/5. So the road coming from one side is at a height of -2/5. The road from the other is -2/5. Then that means that the road from both sides simultaneously would be -2/5. What's our actual function value, though? Our function value is undefined. So let's take a look at the picture here. So now I'm going to make a function, alpha f1 n over d. I'm going to do the graph of x squared plus 4x plus 3. And you wouldn't be able to use a calc on this, but I just want to show you that what I'm saying is not crazy. Okay, let's do a window. Let's go we just want to be around -1, right? So let's go from 0 until no, -2 until 0. And let's go from -1. Let's go -2 until 1. Here's my picture. You see it right there? If I hit trace, I go to -1. We don't have a y value. There's a hole there. Now I'm going to take this. I'm going to turn off this graph. See how that isn't highlighted anymore? That means that graph is turned off. And then underneath it, I'm going to graph x plus 4 over x plus 3 over x minus 4. Watch what happens to my graph. It looks exactly the same, except for one detail. I'm going to go back, and I'm going to turn back on this graph. So both of these are graphed. Look, they're right on top of each other. They're exactly on top of each other, except for one simple point. I'm going to trace. This was my first graph. This is the graph that had a hole at -1. If you push up, it'll jump to the other graph. And now when I go to -1, it takes me to -2/5. -2/5 is where the hole was supposed to be. So what I could say here is F has a hole at -1, -2/5. -2/5 would be the height that I would have to, if I could make up a point. I'm going to go and turn off the second equation again. Clear. This is my graph. If I wanted to fix that little hole right there, what I would have to do is I would have to implement a point at -1 that was at a height of -2/5. Okay, I'm going to pause there and let you kind of get your bearings and then come back and watch the next video where we start to talk about continuity.